All right, guys. Well, here is the TBL notes for the TBL day next week. And this is on the chemical senses, which include both taste and smell. So let's get going. All right, so first of all, we'll talk about the taste portion. And so we'll start with taste buds. The taste buds, infants have a lot more than adults do, about 10,000. And by the time we're adults, we get down to about 3,000. And so here's a couple shots of our little guys when they were trying out all those 10,000 taste buds. This one here, Soren, he loved eating sand, just shoving that sand in his mouth and just crunching down on it. Eve was the same way. Christian a little bit. This is Christian here when he's eating some carrots for the first time. The funny thing about kids is when you first feed them a food, they just make this horrible face that looks like you just gave them some terrible tasting thing, and that's just kind of their reaction to all the new flavors that are coming into their mouth. But then they actually want more usually, so it's kind of funny. So kids are kind of super tasters in a way. So the taste buds themselves are composed of 3 types of specialized epithelial cells, and those types of cells are here. So there's the actual taste cells, the gustatory cells. These are taste receptors. They're not the neuron itself, and so they have several hairs or little microvilli that stick up to increase the surface area. And then there's these little pores, and the hairs extend through these pores, kind of like little holes. Chemicals pass down through these holes and connect to the hairs, which are really what are part of the receptor. And there's only about a 10-day lifespan in these. There's constant turnover, constantly replacing these gustatory cells. Supporting cells are just there to, as the name implies, give support, give shape to the taste bud. And then basal cells are there, the stem cells there, to do all of that replacing of the taste cells from the high turnover rate that was there in the gustatory cells. The tongue itself is made up of a bunch of papillae, which are just bumps on the surface of the tongue. So that's what gives the tongue its rough texture. And most of these, not all of these, most of these contain the taste buds. Taste buds can also be outside of papillae. They don't have to be in papillae. The 3 types of papillae that we'll talk about, there's the filiform, the circumvallate, or just known as the vallate, and the fungiform papillae. The fungiform are the ones that are the most abundant, and those have about 5 taste buds in each of them. The filiform are very small, and they don't have taste buds. They're there more just for giving some friction, some texture. And again, those vallate vallate ones are the largest ones. We only have about 7 to 12 of these. They make a little V on the back of the tongue, but these have about 100 taste buds in each. So lots of taste buds, but we only have 7 to 12. So here's a look at that. Here's those vallate papillae. You can see that V shape that they're making. All these little ones are the fungiform ones, and you can see how the taste bud is kind of coming up right here. Got to get down in there. Chemical gets down inside that, interacts with these little taste buds there, and that's how the neuron gets activated to go send the signal for taste. Okay. So the taste buds themselves are kind of gourd shaped. That's why I have this in the shape of a gourd, kind of larger on the bottom, smaller on the top. Again, there's that pore to let the chemical in. It opens to the surface of the epithelium, type of epithelial tissue, and then gustatory hairs inside that pore, and these are covered in saliva. Locations we find these, most of them are on the tongue, but we also have some taste buds in our soft palate, so that top part of the roof of our mouth, kind of towards the back, our inner cheeks, our pharynx, which is like the back of our throat, and then our epiglottis too, the thing that covers up our larynx when we swallow. And so here's a image diagram, the structure of a taste bud. And again, each taste bud has about 50 to 100 different epithelial cells. And what I'd like you to do is just go to figure 15.4 in your book and label all these different structures and be able to know what all these different cells are and structures are in a taste bud. Okay, so as far as the basic taste sensations, There's really five that we know of. So first one is sweet, obviously sugars, alcohols, some amino acids, and lead causes this sensation. Salty, this is what metals taste like. Sodium chloride is normal table salt. Okay, and then there's sour, and this is things that are acidic. Excuse me. And then things that are bitter um, are things that are typically have an alkaloid pH, so a higher pH. And most drugs are this way, so caffeine, morphine, nicotine, Nurangen, we'll talk about that one in a sec. And so we're way more sensitive to bitter things than we are sour things. And this is really because many poisons in the wild and medicines are bitter. And so it's much more important to have that high sensitivity to the bitter alkaloid substances because those are much more likely to be poisonous, even though we think of acids as kind of the bad things. And then a newer discovered taste known as umami, which is kind of our savory taste, discovered by the Japanese. Amino acid. This is stimulated by amino acids, and so we get this savory flavor from meats. Other tastes that we can have, a minty flavor is kind of an interesting thing. This is actually stimulating our cold receptors, so it actually kind of tricks your mouth into thinking that it's cold. And then spicy foods are similar, but a little bit different. Capsaicin is the main chemical inside of hot peppers and things like that. You might have seen capsaicin in some little creams that you can put on, like sore muscles and things like that. But what this does is it lowers the threshold for stimulation of your warm receptors. So again, you pretty much just feel hot all over your mouth and all over your body. And it kind of just, again, tricks your body into thinking that your temperature is warmer than it is. One thing that's interesting is this idea of a tongue map, saying that sweet is in the front, salty is on the sides in the front, and then sour on the sides in the back, and then bitter in the very back. This is not true. This is just kind of an old myth. All areas of the tongue have the ability to taste all the different tastes that we just talked about. Individual differences, as I kind of mentioned before, there's super tasters. I was saying it in terms of the kids being super tasters, but there actually are people that have a much stronger sense of taste, and really that comes from them having more of those fungiform papillae, and so they're more sensitive to taste. One chemical known as Nurangen is found in grapefruit, and interestingly enough, some people taste it as bitter, and some people don't taste it at all. So some people can just chow on the membrane part of grapefruit and not even be bothered by it, and other people, like me and probably a lot of you, taste that membrane part of the grapefruit, and it's just extremely bitter, don't want anything to do with it. Another interesting thing is as we age, the number of taste buds that we have goes down. So our tastes become less strong. And so as far as the neurological pathway of taste, again, we have the specialized membrane that is the taste bud, and then receptors open to chemicals that cause depolarization. So we're going to send an action potential. All right, so action potential. It's going to go eventually go down the down the neuron, but some tastes use what's known as a second messenger system. We talked about this a little bit before, which is kind of binding to a receptor, and that setting off a whole little chain of events inside the cell, which eventually leads to that message being sent. But then others can directly produce action potentials. So, for example, when we taste salty things, that sodium, that when you eat sodium, it actually just rushes right into the cell, just like sodium rushing into the cell normally would with an action potential, and that stimulates depolarization, it causes depolarization, and stimulates an action potential. So we kind of have both those options in taste. Some of them happen via the second messenger system, some of them happen via a chemical directly producing an action potential. So once we get that action potential on the sensory neuron, it's going to make its way up through the brain, and it ends in what's called the gustatory cortex, which is found in the frontal lobe. And then as far as the cranial nerves go that contain these sensory neurons, the anterior 2/3 of the tongue, so the front part, that's cranial nerve 7, the facial nerve. Posterior 1/3, the back part, is is the glossopharyngeal, cranial nerve 9, and then the ones that are kind of in the back of the throat, those are connected to the vagus nerve, cranial nerve 10. Okay, moving on to the other chemical sense, which is smell. Instead of the gustatory epithelium, we have the olfactory epithelium. So again, it's epithelial tissue, specialized epithelial cells. Most of these are found in the superior concha of the nose. All right, so these nasal concha right here, the superior part of it right here. It's only about 5 centimeters squared of area where we have this olfactory epithelium. But in that area, there's about 10 to 20 million olfactory receptors, so a lot of receptors. Nowhere close to the eye, where it was over 100 million, but still quite a bit. And interesting part is it kind of requires this hairpin turn to hit the receptors, and that's exactly why we sniff when we forcefully suck air up into our nose, instead of it just kind of nicely going this way. When we suck it, it kind of churns it up, and with that sniff, and that moves it up towards the receptors, so we actually smell it. So the cell types in the olfactory epithelium, again, we've got the receptor cells. These are bipolar neurons. Again, very constant turnover, 60-day lifespan of these, a little bit longer. And then olfactory hairs are cilia, just like in the gustatory ones, but there's a mucus film in these, and when that chemical that we sniff in hits that mucus, it dissolves, and then that allows it to interact with the hair cells. And then there's supporting cells holding everything together, giving it stability and shape. And then we have basal cells, which again are the stem cells for the olfactory receptors, so very similar to the gustatory cell types. And you can see those here. So again, you can go to figure 15.2 in your book and label all of those and be familiar with the ones there, A through F. And as far as smell goes, as I said, we only have about 5 typical tastes that we can sense. But as far as smells go, it's literally somewhere around 10,000 different odors that we can detect. And so neurons are stimulated by different combinations of a lower number of chemicals, only about 7 to maybe 50 chemicals, but it's all about the different combinations of each one. And the research in this area is hard, and we obviously, if the range is 7 to 50, we don't really have that good of an idea about how all this works. What it requires for us to actually smell something is what's known as a volatile substance, which just means it's in its gaseous state. It's in the gas. It's turned into the air, right? And then it hits that mucus and dissolves, and then it can be sensed. And so the pathway here for smell is the molecule will bind to that membrane receptor, and that starts the second messenger system. That second messenger system eventually opens an ion channel, which eventually depolarizes the olfactory neuron, and then that creates an action potential, right? And then the olfactory neuron stimulates neurons in the olfactory nerve, right? And that's that olfactory bulb that comes down. We saw that in the brain last semester. Interesting part is one track goes directly to the olfactory cortex, so the temporal lobe, and then the other track goes to the hypothalamus. This is where our emotional responses to smell come from, and then also to and through the limbic system. This is the limbic system, especially the hippocampus, is very important for memory and emotions, and so you can see why smells trigger memories and emotions for us so commonly. And interestingly enough, the right nostril has more emotional connections to smells, whereas the left nostril is more accurate. That has to do with the idea of right-brained. The right brain is more involved in the emotional, artistic side, whereas the left brain is more involved in scientific, quantitative reasoning. And so a couple things about individual smell differences. There's some genetic differences with smell. For example, cilantro. Um, some people can't smell it at all. There's just no smell when they smash some cilantro and try to smell it. They just don't smell it. But those people taste it, it tastes like soap, and so they typically will not like cilantro. Another interesting one is ethyl mercaptan, which has this garlicky, rotten egg smell for most people, uh, and but some people can't smell it. And this is actually the chemical that they put into natural gas or propane just to make it so you could smell it. Natural gas naturally has no smell to it at all, but they put that chemical in just so people will be aware of it when there's a leak. But some people can't smell it, so it can be dangerous for those people. Another interesting thing, just like smell, or just like taste, um, your sense of smell declines with age. All right, and then lastly here, a condition known as anosmia, which just pretty much means loss of smell sensation or reduction of smell sensation. This can be congenital, would come from underdevelopment of the olfactory bulbs, or it can be caused by trauma. Crushing of that cribriform plate, which, if you remember, that was part of the ethmoid bone. Can be in a car accident, could be some kind of blunt trauma to the face that can smash that in your nose. Also, breathing in super toxic chemicals can destroy those basal cells, and those are the ones that are there to replace the smell receptor cells. So if those are destroyed, they can be you can lose all of your smell receptors. Zinc is a very important part of the chemicals in the smell receptors. So zinc deficiencies can cause that. Also, neurological disorders like Alzheimer's, Parkinson's, schizophrenia, and then some medications can destroy the sense of smell. And so that wraps up our TBL day. We'll see you all next week.